Hello and welcome to our very last lesson of Calculus and Vectors. We are wrapping up not only Unit 6, but our entire course today. And so today's lesson is distance. We are going to be able to determine the distance between points and lines and planes, as well as to understand what they mean in terms of their graphs as well. So starting with the equation for distance from a point to a line. So we have point P0, which is given to us. So x0 and y0 are known, and the line in Cartesian form, ax plus by plus c is equal to 0. And the distance, which is d, is given by this equation here. So here we just have a times x0 plus b times y0 plus c, and we're taking the absolute value here and dividing this by a squared plus b squared and the square root of this. Now, one thing here, point P0 is not on the plane, or sorry, not on the line, because if it was on the line, the distance would just be 0. And so actually you will find that d will be equal to 0 when the point does lie on the line. But if it's not on the line, then you can use this equation to determine the distance between the point and the line. Now, I am going to show you just for this one how we find this formula. So consider this as our diagram. So this is the line given by ax plus by plus c is equal to 0, and this is our given point. Now, first we consider a perpendicular line from the point to the line. So the shortest distance from point P to the line is the line that is directly perpendicular to the line. And when we find D, the distance, that's exactly what we're finding. We want to find that shortest distance. And so this distance is going to be the magnitude of PQ here. And PQ right now is just as a line segment. Now, consider also the normal vector to the line, which, considering our line is in Cartesian form, then the perpendicular vector or the normal vector is just AB, given from or taken from AB in the equation. Now, the vector from Q to P, or QP, now putting it as a vector, is the difference between the x components and the y components. So x0 minus x1, y0 minus y1. And because PQ is perpendicular to the line, then we know that the vector QP is also parallel to the normal vector, which means that it is also a scalar multiple of this parallel vector. And so QP as a vector can be written as K, and this should be a vector here as well, times the normal vector. So K times A, B as a coordinate for some scalar K. Now, what we really want to do is find out what that K is, because we have A and B, but because we're trying to solve for QP, or the distance D, we need to determine that K. Now, we know that Q is on the line. It's a point on the line. So that means it satisfies our Cartesian equation. So ax1 plus by1 plus c should be equal to 0. Now, going back here, knowing that QP is equal to K times AB, and also using the fact that QP is this coordinate here, using these two equalities here, I can actually end up with x1 is equal to x0 minus k times a. Okay, the reason for this is we would say these two are both QP vectors. So x0 minus x1 is equal to k times a. So then solving for x1, I will just have x0 minus k times a. Similarly, y1, which is the y coordinate of point Q, is going to be y0 minus k times b. Now, substituting these two values of x1 and y1 into our Cartesian equation, we end up with a times x0 minus k times a and b times y0 minus k times b. And then c is just there. Now, distributing this and trying to simplify it, remember, a, x0, and y0 are all given to us. And same with b and c. These are all given values. The only unknown here, and pretty much what we're trying to solve, is that k. So I will rearrange all of this to try to solve for k. And k will be equal to a times x0 plus b times y0 plus c divided by a squared plus b squared. But we're not done yet. We want to find the length or the magnitude of vector PQ, which is equal to D there. And so the magnitude here, knowing that PQ was equal to K times the vector N, is going to be the absolute value of K. Oh, and again, this should be a vector here, times the magnitude of vector N. Now, vector N being AB, we can find the magnitude as square root of a squared plus b squared. And this is just K, and we took the absolute value. Now, all I've done is simplify this with the denominator here, and I end up with square root of a squared plus b squared. And this is precisely this formula that I just gave you up here. And so that is how this formula is derived. And now we're actually going to start using it just with given points and lines. So our first example here, we have point P as 6, -4, and we want to find the distance to the line with the equation 5x minus 2y plus 13. So x0 here, which is our given, is 6. y0 is -4, and a is 5, b is -2, and c is 13. So substituting all of these values into my formula here, I end up with this expression here, and simplifying, I have absolute value of 51 over square root of 29, which is approximately 9.47. Now, because we are working with just points and lines in just any space, we don't really have units here. So we just say the distance from the point to the line is approximately 9.47. So again, no units. Next example, we are given the point, but now our equation is in vector form. So we do have one more step here, which is to convert this into Cartesian form. Now, the way I'm going to do this is I start with the parametric form, which is x is equal to -2 minus 4s, and y is equal to -1 plus 3s. Now, this is the symmetric equation. So these are both equal to s. So all I've done here is move everything over in order to isolate s, and same with here, I isolated s. And so x plus 2 divided by -4 is equal to y plus 1 divided by 3. Now, this is just multiplying, butterfly method, cross multiplication, different names for it. If I multiply these two, then I end up with 3x plus 2 is equal to -4 times y plus 1. And if you distribute and rearrange this to get the Cartesian form, you will end up with 3x plus 4y plus 10 is equal to 0. And now I have a, b, c, and I had x0, y0, so I can actually just substitute into my formula for d, and I will end up with absolute value of 28 over square root of 25, which is just 5, and this is approximately 5.6, or actually no, this one I think will end up, yeah, exactly 5.6. So then we just say the distance from the point to the line with this equation is just 5.6. When you are rounding, it is important here to add approximately to show that it is not the exact value, but in this case, it will actually end up being as an exact value 5.6. So that's why we can say it is 5.6. Now, this next example, we have to calculate the distance between two parallel lines and given by these two equations. We can actually do this as well, because when you have two parallel lines, these two have a distance between them, right? So sometimes it is good to know what that distance between these two lines is. Now, knowing what we know, we don't have all the pieces of information, but we can derive those the information that we do need from what we are given. So all we have to do is find one point on one of these lines, and then we have a point that's not on the other line, and then we have a point on the line, and we can use the distance formula. So it doesn't matter which one you use, but I picked the first line, so 4x plus 7y minus 20 is equal to 0. And the simplest point that you can find is the x-intercept or the y-intercept. So I chose the x-intercept here, so I let y is equal 0, so that 4x is equal to 20. And so the x-intercept occurs at 5, 0. This is now a point that is not on the second line. So now using the distance formula, I will end up with 40. This is also absolute value, but because I have already checked it, I can just write 40 and over square root of 65. And this is approximately 4.96. So then the distance between the two parallel lines is, oh, I just said it and I didn't add it myself, but approximately 4.96. Now, I'm going to show you, and we did do this example here where we converted the vector form into Cartesian form, but there's actually a way to solve the distance when you are given your line in vector form as well. So remember we have our vector form R, and this is going to be our reference point plus a parameter S, so S is in the set of real numbers, times our direction vector M. Now, if you have a point P, and you want to find the distance to the line, this distance can also be the absolute value of the cross product of the direction vector and QP. So the reason for this is, consider this diagram here, right? This is point P, and Q can be any point on the line. And so again, we've drawn that shortest distance between point P and the line, which is formed by the perpendicular line. And so using this diagram, the distance from point P to this line can be found as D, but D is also part of this triangle here. Now, sine of theta, which theta is this angle here that's between Q, P and the line, is given by D divided by the magnitude of QP. So QP is our hypotenuse there, because remember, this is also on this side, we have a right triangle. So from the cross product as well, we know that M cross product QP and the magnitude of, or the absolute value of this is also equal to this expression. So the magnitude of M times the magnitude of QP times sine of theta. And again, comes from the triangle property. But we just found out from here that D is equal to sine of theta times magnitude of QP. So then really, this part is just D. So this is equal to D, so that we have magnitude of M times D. But remember, we were trying to solve for D, so we start with this one, which is the cross product of Q, P times M. We take the absolute value here and divide it by the magnitude of M, which is exactly this formula above. So you can also try this example that we just did now with this new formula and see that you get the same answer. But I'm showing you one more example here. So we have the point 413 on this line. So this is M now, our direction vector. And we also have the point Q. So this is point Q, the easiest point which is given to us on the line. So the first thing we do is find QP as a vector, which will be 3, 2, 1. And then we find the cross product of QP, vector QP, and the direction vector M. And this one I've just shown you or given you the answer, but do try it on your own if you're not sure or you just want to double check or you just want extra practice with cross product. And you will get -5, 8, -1. Now we can find the magnitude of this and the magnitude of M. So this here will give us -5 squared plus 8 squared plus -1 squared, and the square root of that is 90, or square root of 90. And the magnitude of M will give us square root of 9, or just 3. So then D is just square root of 90 divided by 3, and this is square root of 10, or approximately 3.16. So then the distance from this point to this line is approximately 3.16. Now, I'm going to show you one alternative solution for this one as well. So consider, again, same point and same line. Consider the parametric form of this equation. So x is 1 plus 2t, which is 1 plus 2t, y is negative 1 plus t, and z is 2, negative 2t. Now, we construct a vector A, and it's from any general point on the line to point P. So now we're not just picking point Q, we're picking a random point. And remember, any random point will have will satisfy this parametric equation. So it will have an x that will be 1 plus 2t, a y that's negative 1 plus t, and a z that's 2 minus 2t. And so the vector from this point to point P can be given by 4 minus, this is now x, 1 minus, this is y, and this is z. And 4, 1, and 3 were just from point P here. And if you simplify this, you will end up with 3 minus 2t, 2 minus t, and 1 plus 2t. Now, this vector here, going back to my diagram here, so consider this is point P, this is your line. This will be AP, or this will be vector A, which is formed by any point now. And again, here Q is just a general point, so this is that vector there. Now, we want to find the minimum distance. So remember, to find D, that is the minimum distance between the point and the line. And at this minimum, to find this minimum distance, then we want to find the point, the random point, that A will be perpendicular to the line. So in other words, knowing the direction vector M, this will have a dot product of 0 with A. Now, taking that dot product there, so this is vector A, which is, again, think of it as like PQ for a random point Q. And this is your direction vector. Now, we want this to be equal to 0. So 2 times x plus 1 times the y minus 2 times the z will give you 6 minus 4t plus 2 minus t minus 2 minus 4t is equal to 0. And simplifying this and solving, you should get t is equal to 2 over 3. So then the minimum distance occurs when t is equal to 6 over 7 at the point, this point. So now all I'm doing is substituting back this value of, oh, sorry, this should be typo. This should be 2 over 3. So then substituting t is equal to 2 over 3 into this coordinates that I had here, and I will end up, or sorry, not into this coordinate. I use the equation of the line because I want to find that the point there. So then this will give me 0.7 over 3, negative 1 over 3, and 2 over 3. So again, think of going back here to this diagram. You are actually, in fact, now finding what point R is, because this is the point at which P intersects with the line, and it gives you the shortest distance here. Now, having found point R here, the distance between that point, so again, this is point R, and point P is given by, we can find just the magnitude of this vector, and this is given by this expression here, which will, if you simplify, give you square root of 10. And that's exactly what we had up here, square root of 10, or approximately 3.16. And now, actually, I've shown you 3 different ways that you can find the distance from a point to a line in vector form. Remember, one of them was the first one, which is to convert to Cartesian form, or you can use this formula here, or you can set up your own point R, which is the closest point to point P from the line, and you can find the distance between PR. Our final concept here is the distance from a point P0, again, given to us, to a plane AX plus BY plus CZ plus D is equal to 0. Now, I'm not going too much into how this one is derived, but if you follow the very first part, which was distance from a point to a line, and how that formula was derived, this is very close to that method as well. So, and you can see even the equation is very similar as well. Now here, because we have a plane, we do have z here as well. So in the numerator, you have the absolute value of ax0 plus by0 plus c times z0 plus d. And in your denominator, you have a squared plus b squared plus c squared, and taking the square root of that. Now, consider here, this is your plane, and this is the point P0. Again, same idea as how we derived the formula above, but we have this point that's on the plane, and we use what we know about the normal vector in order to be able to find this formula. So now I'm just going to show you a few examples of how we use it. So here we have a point P given by 4, -1, 6, and the plane 2x minus y plus 2z minus 9 is equal to 0. Using the formula, we get 12 over square root of 9, or just 3 here, and 12 divided by 3 is 4. So the distance between the given point and the plane is 4 here. We can also have we can find the distance between, oh, this should be two parallel planes, sorry. Two parallel planes, and this is the same idea as two parallel lines. So here you find one point on one of the planes. So the simplest one is any of the intercepts. So let's pick the x-intercept here. So y is equal to z equal to 0, and the x-intercept occurs at 2, 0, 0. And because their d values are different, then we know they are parallel planes. Even if this was not given to us, we can see that they have the same normal vector, but they have a different d value, so they are not coincident planes. So using that formula above, I will set up by just substituting all my values of x0, y0, z0, as well as a, b, c, d, and I will end up with 21 over square root of 49, which is also 21 over 7, and this is equal to 3. Now, we also have sometimes, another type of example. For the two planes above, you might be asked to find the equation of the plane that is equidistant from the two planes, which means an equal distance apart. Knowing that they have a distance of 3 between the two planes, that means if you have two planes like this, you want to find the one that's directly in the middle, so it will be an equal distance apart from each of them. So this plane, firstly, will be parallel to both pi 1 and pi 2. So that means you can already set up the Cartesian equation, so 2x minus 3y plus 6z, and all we have to do is find d. And d will be in the set of real numbers, so it is a scalar. So we have the x-intercept from the first plane, so we find the x-intercept of the second plane, and it will be -17 over 2. Now, because this plane is an equal distance apart, that means its x-intercept will also be an equal distance apart from plane 1 and plane 2. So it will be the midpoint. And finding the midpoint there, you will get -13 over 4. Now, I will just substitute this back as if I'm solving the x-intercept for this new equation here. And substituting, you should get y and z are going to be 0. So 2 times -13 over 4 plus d should be equal to 0. And solving that, you get d is equal to 13 over 2. So then the equation of the plane that is equidistant apart from plane 1 and plane 2 is given by 2x minus 3y plus 6z plus 13 over 2. That's just the d value we found. And again, remember, we don't want to work with rational numbers, so I just multiply everything by 2, and my new equation is 4x minus 3y plus 12z plus 13 is equal to 0. And one more example here. We want to find the distance between these two lines here. So right away from their direction vector, I know that these two are not parallel, and you can check that they will actually be skew lines. So I'll leave that for you to confirm. But we might want to find the distance between the two lines. So how we do that, we actually will make these into planes. So I will create another vector here that will be parallel to line 2. So this is line 1, this is line 2. And now this is another vector or direction vector that is parallel to L2. And so its direction vector is the same as L2, so 1, 1, 2. Similarly, for L1, uh, for L2, I use the direction vector of L1 to set up now another plane. And so I have now two planes. So when you're finding the distance between two lines, well, pretty much you form two planes using their direction vectors, and you will find the distance between these two planes because now we just learned how to do that. So having these two planes now, and you only really need one of the planes, so I can just stick with plane 2. So I will find the normal vector, which will be the cross product of M2. So this is just the direction vector of line 2, and B, which was the direction vector of line 1, because I wanted these two planes to be parallel. So finding this cross product, I end up with 3, 1, 2, and now this actually is my setup for the Cartesian form of the plane 2. So then I have 3x plus y plus 2z plus d is equal to 0. And from line 2, I already had the point 0, 1, 0. And so substituting that in, I get d is equal to -1. So then plane 2 has the equation 3x plus y plus 2z minus 1 is equal to 0. And this is also, because it is the direction vector of both of these lines, it is actually perpendicular to both of these lines as well. So it will be precisely the distance between the two lines. And now I have a point, I have my plane, so I can use the distance formula as follows to find that the distance between these two lines is approximately 1.60. And that was the very last example of our lesson, as well as our entire course. It has truly been a pleasure teaching you. I hope you learned a lot from calculus and vectors. And as always, don't hesitate to reach out if you have any questions. Best of luck on your summative assessment for Unit 6. And you just have to now complete the culminating project, which is really exciting. So it will be a wrap up of everything we learned throughout this course. And I will hopefully see you in any other courses that you take, and best of luck with whatever you do after calculus and vectors.